This is a new video, as you can tell, because Chapter 5 has changed. So this is going to be the current set of slides. So we're going to do Chapter 5. It's split into two sections, so it's a really short chapter. I'll show you how to do all the stat key and how to do everything on the calculator as before. So today, as you can see, we're going to use PowerPoints, the calculator. I got a fun little whiteboard I'm going to draw on here. And of course, there's stat key. So let's get started with the slides. So just as a quick introduction, there's really only two things we study. And the topic of the chapter is normal distributions. So we're going to learn about those. Then we're going to do some hypothesis testing and some confidence intervals in the next section. So most of this chapter uses concepts from chapters 3 and 4. So theoretically, it's a lot of the same stuff. However, in application, we're going to be doing different things inside StatKey, and of course, as you can see, we're going to be using the graphing calculator. So let's jump right in. So a couple definitions before we get going. One of them is we have to define what's called a continuous variable. We never really messed with this before, even though we did draw smooth curves, but we just called them bell-shaped curves. If you recall from Chapter 2, we had a few smooth curves. But we're going to do a special kind of smooth curve that's called a density curve. So continuous just means that any value in the interval, like in some interval, is a valid value for the variable. This is used a lot for things that are measurements like height and weight and things like that. What it really means is that there's no amount of precision that's considered too precise. So if you tell everybody that you're, 64 inches tall or whatever, that's not a precise measurement. You're rounding that based on, you don't want to include the fractions, and that totally makes sense. But we understand that height could be any value, right? There's no such thing as, telling somebody that they can't be 64.256 inches tall. Of course that could happen. It just depends on how accurately you want to measure it. So what we're saying here with a continuous variable is that there's no limit to how much accuracy. So it's a really technical condition, but just it is something you have to keep in the back of your mind as we work through these. So a theoretical model for the distribution of a continuous random variable is called a density curve. So a random variable is just what we've called a variable. This is just a more specific name of it, a random variable. And here you can see that we have a histogram shown just with some variable that's being measured, but we could overlay some sort of distribution. It doesn't have to be bell-shaped. In this case, we're going to be looking for things that are bell-shaped. And we can just replace the histogram or the dot plot with this density curve. So when we put a density curve in place of whatever we have, we just scale it. And that's what it says on the next slide here. So when we superimpose a density curve, what we do is we change the y-coordinates so that the total area under the curve is equal to 1 to correspond to 100% of the distribution. Basically, instead of doing a frequency count like we would do for a histogram, it becomes a relative frequency count. All you do is you take the height and divide it by the sample size. Now, StatKey takes care of that for us, so you don't really have to know how to do that, but just know that when we see a density curve, it will have decimals on the left side. And number 2, the area over any interval is the proportion of the distribution in that interval. So that just means the size of the area in terms of its measurement is proportional to how much space it takes up. And we're going to use technology to do these areas under the curve. When we draw pictures, we're going to have to draw pictures by hand. And StatKey will do that for us, obviously. StatKey is very good at making graphs. And we'll use the graphing calculator to compute the probability. So we're going to be doing 3 different things, right? Graphing calculator, drawing pictures by hand, and StatKey. So here's a picture of the normal distribution, and you might think it just looks like any old bell-shaped distribution, because it basically is just a generic bell-shaped distribution, but it has some special properties. One of the properties is that it pops up naturally all the time in naturally occurring data sets. And so what happens is, because it's so popular in terms of like where it appears, that a lot of times we tend to use it even if the data are not bell-shaped. There are conditions under which we can use this because it's well understood. So here I have this demonstration. I'm going to show you this demonstration at the end of the slideshow. But if you want to click on this now, pause the video and click on this now, open up the PowerPoint and just give it a click. You'll see it takes you right to this demonstration. Or just wait till the end and you can follow along with how I do it. But essentially, this is the Price is Right game, Plinko. Some of you might catch that reference, where these bouncing balls just randomly move to the left or right as they hit these little pegs. And it turns out that it actually creates a normal distribution, which is pretty interesting. So more on that later, but just understand that it does naturally occur. So when we look at graphs of these normal density curves, we use this notation. And I know there's a ton of notation in this class. You guys should be used to it by now, let's hope. N just means normal. And then whenever you see parentheses in a math class, it usually means that this is a function. So the things in here are called the parameters, right? Mu and sigma are parameters, as you've seen before. So we're just saying for any normal distribution, if we specify the mean mu and the standard deviation sigma, that completely determines what the graph will look like. So normal density curves can really only take a few different forms. If you change the mean, it shifts to the left or right, which makes sense, right? Because the amount of variability doesn't change if sigma stays whatever number it is. So you can see in the example here, the standard deviation is 1 in both of these graphs, but the mean changes from 0 to 2. And so you can see the one that's 2, moves over to the right. But over here, you can see these all have the same mean. The mean is 0, and the standard deviations are all different. So when you change the standard deviation, it has to... So if you increase the standard deviation, the height of the graph has to drop because the area has to stay the same. The area under this has to equal 1. So shrinking it will pull it up, and then expanding it will bring it down so that it remains constant amount of space taken up under the curve. So for a normal distribution, this is all you need to know. Changing the mean moves it left and right. Changing the standard deviation makes it expand and contract. And that's all we use it for. We are going to deal almost exclusively with the standard normal distribution. And that's what happens when the mean is 0 and the standard deviation is 1. So it's called a standard normal distribution because it's been standardized. So we can move between other normal distributions and the standard normal by making what's called a transformation. It's a quick little algebra thing, which you've seen before, and it's coming up. And as before when we did z-scores, we used the letter z. So this little tilde here just means, this symbol here means in math, distributed according to. So we're saying that this z distribution is distributed according to normal with a mean 0, standard deviation 1. So there's a lot going on in that little notation. So to convert from an x value, so x is where our measurement is, right, on any normal distribution, to a z value on a n01 distribution, what we do is we just standardize the values. And you've seen this formula before in Chapter 2. But in Chapter 5, we use this special form where these are the parameters here. We don't use the sample statistics here. Now later on we will, but we will get there when we get there. So if you know the parameters, mu and sigma, you just plug them in. And of course x is just the data value, whatever it happens to be. But we're not looking at data sets in Chapter 5. We're looking, specifically, we're going to be doing hypothesis testing. Whenever we have hypothesis testing, we're looking at sample statistics. So we're going to have to look at the distribution of sample statistics. So this is just a, like I said, a generic formula, which we'll be filling in later with the stuff that we would get from our samples. And as you probably guessed, we're going to be doing a lot of technology. And in general, the way the technology works here is you put in the mean and standard deviation for the normal distribution. You may be asked to put in a mean and standard deviation for something other than the standard normal. Just follow the instructions on the homework. I'll show you how to do it for the standard normal. It works exactly the same for other distributions. You will also be asked to type in the endpoints of the interval. This is the trickiest thing in Chapter 5. It gives people a lot of trouble. Just pay attention. You should be fine. And then you have to type in the direction. So whether you're on the calculator or on StatKey, you still have to specify this information. So here's how it works. Here's the actual instructions. I just want to go over this real quick. I'm going to show you how to do it live, but here's your reference guide. So on the TI-84, I'll just show you what to type in, like how it works over here. Let me clear all this out. So second distribution, that's above variables. Oh, this looks a little weird. So it's down here. And it takes us into these distributions. We want normal CDF, number 2. And just press Enter, and it'll take you to this screen. If you have a TI-83 or 85, it takes you to a different screen, but the directions are still the same. Type in the following 4 values in order. So you can see lower, upper, that's what I call the left and right endpoint. Mu and sigma, those are mu and sigma. So you're just going to type those 4 things in order. We'll fill this in when we get to the examples. And then you press paste and enter, and it'll go. If you have a TI-83 or TI-85, you don't press paste. It just does it automatically. Now, we already know how to deal with left tail, right tail, and two tail. But when we do it on the calculator, you only type in left or right. If we get a two tail, you just do left or right and double it. You don't do left and right. It's one or the other, and then you double it, just like you did in StatKey in Chapter 4. You type in the sample statistic once, and if it's two-tail, you double it. And we're going to talk about how to use large negative numbers when we get to the example. So here's how we do it on StatKey. Again, I'll show you how to do this. This is very, very similar to what you saw before, but this reference is here for you. So let's go ahead and get into one of these examples. When you guys are following along at home, I highly, highly, highly recommend that you follow the instructions that I'm giving you, because this is the stuff that's going to be on a test. I need you to be able to draw these curves by hand and fill in where the sample statistics are. Now here we have z-scores. So these are actually what's called test statistics. More about that later. But just think of them as statistics. They're just things that are measured from a sample. So we want to sketch the standard normal distribution, label the mean, and shade the appropriate region. So the first one we're going to do here is the area above z equals negative 1.51. So this is the way we do it. So here's my little drawing tableau, and I'm just going to select my little black pen. Oh, I can't draw very well. Close enough. So you just, on a piece of paper, want to draw, something that looks like that normal distribution that I showed you a second ago. And then you want to label the standard deviations, right? So on a 0, 1 distribution, so this is a standard normal, right? Z, so it's Z tilde N 0, 1. So our standard deviation is 1, and our mean is 0. So I'm just going to go ahead and label everything. 0, 1, 2, negative 1, negative 2. This is the same stuff we did in Chapter 2. We just used data in Chapter 2. Here we're using what's called a theoretical distribution. So if you go back and look at the problem, the way it was posed, I need to find the area above z equals negative 1.51. So this is the mean, clearly right here, 0. Negative 1.51 is over here, pretty much. And then further look at the instructions. We want the area above z equals negative 1.51. So above means to the right. So you really only have to shade it like this. You don't have to like color it in like it's a coloring book. So the reason we do these shadings is because this stuff gets a lot tougher in Chapter 6. In Chapter 5, you are told exactly what to do. But in Chapter 6, you have to decide left tail, right tail, two tail. You have to decide hypothesis test or confidence interval. You have to decide reject the null or do not. Here, we're basically told what to do, so it's fairly straightforward. But just understand that drawing these pictures will help you a lot. If by this point in the class you're still overestimating your own ability, you might want to dial it back a notch and do what I'm asking you guys to do. Trust me, you will be happy. So now we're ready to go over to the calculator and type everything in. So we have to specify two endpoints. And in the notes it says that for a right tail distribution, so this is clearly right tail. So I'm going to go ahead and write that in, right? This is right RT. This is right tail. I know it doesn't look like much of a tail, but that's what we call it, right? When we shade to the right, it's called a right tail. The lower endpoint is negative 1.51, right? So negative 1.51. So this is our lower. So this is our left endpoint of the distribution. Now, if we look at the upper, this thing just keeps going on and on and on to the right. So in reality, it's actually infinity, but we're not going to type in infinity. Just type in a really big number. So I'm going to type in 10,000. It works fine. If you're not convinced that that's a big enough number, then put in 100,000, put in a million. I don't care. The calculator defaults to 0, 1. And then you go down to paste and hit enter. And you see it like puts it up on the screen. Right? And you can see we get 0.934. Follow the directions on the homework for the number of decimal places. I'm just doing 3 just for illustration, but always follow the homework. So there you go. So that's how you do it. Now what we're going to do is check this answer in StatKey. As you can imagine, StatKey is much faster. So let's go ahead and do that. So the way you do this in StatKey is we're down here in theoretical distributions, normal. All of these instructions are in the notes. I'm just showing you how to do it once each, and then you'll be fine after that. And then what you do is you edit the parameters. In this case, it defaults to 0, 1, so you don't have to change anything. We know we have a right tail distribution. And then just like you did with hypothesis tests, you just change the bottom number. So it's negative 1.51. And you can see it's 0.934. So obviously this is much quicker. And the graph looks about the same. So this is an interesting thing you want to think about. It's sort of how these graphs work. You want to use StatKey to check whether you're drawing good graphs. You really, really do. Hold on, let me shrink this down. And then you can kind of check our answers, right? So again, it's my drawing was, kind of more like spread out because I don't have a scale. The screen in StatKey like fixes the scale. But you can see it just has to be approximate. You want to try to get close. So we can see that this is almost all of the area. So it's 93.4% of the area. That's why we sketch these pictures. And you can see from on the PowerPoints that I have all that stuff all ready to go. All right, let's do the second one. The area between z equals 1.1 and 2.1. So let's go back here. I'm just going to start over. It's just quicker. So everything's the same, right? Draw a nice little curve. 1, 2, 3. 1, 2. And then just label everything. 0, 1, 2, negative 1, negative 2. And we do the same thing here. So we want to know the area between 1.1 and 2.1. So 1.1 is like right about here. 2.1 is like right about here. Now, if you want to like really get specific with it, what you can do is just draw little arrows and write 1.1. Draw a little arrow, write 2.1. It's up to you, just if you want to like remember how it goes. So we're looking for the area between here. So it doesn't look like it's going to be a big area. So if you're doing that on a piece of paper, try to draw it and make it look nice. It doesn't have to be perfect, but just it should take up, it looks like about 10% of the area, maybe 15, something like that. And then, of course, we go into StatKey and double check our answers. So the parameters stay the same, so I don't have to worry about that. So all you have to do is just reset the plot. Now, this is not a two-tail. If I click two-tail, it looks like a confidence interval. That's not what the picture shows, right? My picture definitely shows this chunk off to the side. So what you have to do is a left tail and a right tail and change them separately. This is something you did not have to do with hypothesis tests because this would never happen. And the way that StatKey shows how this works is it creates two different tails, but it creates three different regions. So here's the area to the left of 1.1. Here's the area to the right of 2.1, and this is what's left over, 0.118. And that's about what we thought, right? It looked about 10% of the total size, maybe 15. And that's how you do it. Oh, forgot to do it on the calculator. Well, it's real easy. You can see what to do. So again, it's going to be second variables, so distribution, normal CDF. This time our left endpoint is 1.1. Probably going to do it on the screen. Yeah. Our right endpoint is 2.1. Again, our mu and sigma don't change. Enter, 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 enter. Right, and it's 0.118. So as you can see, both methods are pretty easy. The toughest thing to do is if you have a one-tailed distribution and there's no right endpoint or no left endpoint. For here, we have the right tail distribution. We had to type in a big number for the right tail, and it just means it's way, way, way down the tail. When you're finding areas in between, it really doesn't matter because the endpoints are given, right? Our endpoints here were 1.1 and 2.1. So that's pretty much what you got to do in Chapter 5 that's different than what you did in Chapter 4. It's not that much different. It's just this one extra step. So basically, we no longer use StatKey to generate randomization distributions. Instead, we're going to find out what this z-score is, shade the appropriate region, draw the picture, and compute what will become the p-value. All right, back to the slides. Yeah, in chapters 3 and 4, we saw that nearly all of the distributions of sample statistics were bell-shaped, and that was not a coincidence, right? One of the reasons we, talked about why we use the techniques we use is because we want bell-shaped distributions to either use the 95% rule or to use the standard error that appears there. And it turns out that a lot of these distributions actually follow a normal distribution. So that's why we're using this normal CDF, because we're just going to practice using the normal distribution. So the way this works, if you are given the standard deviation of the data set, or you are given the standard error of the randomization distribution, then the data follows a normal distribution. Later on in Chapter 6, we're going to see another distribution that is bell-shaped, but we don't have to worry about that right now. So here's the first major mathematical principle of this entire class. It's called the central limit theorem. For random samples with a sufficiently large sample size, the distribution of many sample statistics can be approximated with a normal distribution. It's pretty straightforward. It just means if the samples are large and random, then we can overlay this theoretical normal distribution and use its properties instead of relying on a randomization distribution. That's it. That's all it says. And we will see in Chapter 6 what sufficiently large means. For now, we're not going to worry about that. So you can see here's a picture of a randomization distribution with a normal distribution overlaid on top. And we know, for example, if it's let's say you have two categorical variables, your your parameter would be P1 minus P2. And that would your randomization distribution would be centered at 0. And that you can see here that this one is centered at 0. And so whatever the null parameter is, that's where it's centered. This one just happens to be centered at 0. Okay, some of them are centered at 0.5 or 30 or whatever the null parameter is. And as we've discussed before, there are 3 different null parameters. If you have more than one variable, it's centered at 0. If you have one variable, it's centered at either mu 0 or p 0. And notice here that we need the standard error. Sometimes you can make a randomization distribution and just read the standard error off of there. And that's normally what we do. Or you could be given the standard error. That's another thing we can do. So if you have the standard error, either from a randomization distribution or it's just given like all by itself, then we compute what's called a standardized test statistic. So this is just a different version of the same z-score that we talked about a little bit ago. So your sample statistic is what we were calling X in the formula a few slides back. It's whatever is observed from the sample. So the sample statistic is observed in your sample. The null parameter is where the distribution is centered, and the standard error is the amount of variability in your randomization distribution. And what ends up happening is that you just do this calculation, and then you end up doing this stuff. So here, this might be a p-value, this 0.934, and this might be a z-score. So we've already done like the calculator and stat key part. The only other thing you need to do is compute this stuff by hand. And as you can see, it's not a extremely tedious calculation because you're given everything in these problems. You don't have to, you might have to compute the sample statistic by hand, but that's okay. But you have to be given the null parameter and you have to be given the standard error or you can't do it. So when you use what's called a test statistic, like we see here, the p-value is the proportion of a standard normal distribution beyond this test statistic in the direction of the alternative hypothesis, or double the tail for two-tailed tests. This is exactly what we did in Chapter 4, right? The proportion of the distribution. In Chapter 4, we said it's the proportion of red dots. Not that much different, right? So this should look familiar, even though you haven't done this exact calculation before. It's not that much different than what you did do. This slide here is just a really technical condition that may pop up on a test or something or a quiz, that p-values mean different things in different situations. When we have randomization distributions, the p-value is the proportion of our randomization statistics. They give a statistic at least as extreme as the observed sample if the null hypothesis is true. That is from Chapter 4. I did not change it. Density curves, all it does is it changes, instead of proportion of statistics, it's proportion of the overall distribution, like how much area it takes up. But the rule of thumb version of a p-value doesn't change. It is a measure of how extreme these results would be if the null hypothesis were true. So we use the p-value to summarize strength of evidence against the null hypothesis in favor of the alternative. So it operates the same way, but we're not counting dots. We're letting stat key or the calculator add up all these areas and just give us like a size instead of a number. All this is the same. I just put it back in here so you guys could use it as reference. So follow along with that when you're ready to do the homework. I'm going to go ahead and just get to the demonstration. This is all exactly the same as well. So let's do sort of a full problem all the way through. So notice that you've been given the null and alternative hypotheses and all of the sample statistics. If you look at the formula only needs sample statistic, null hypothesis value, and standard error. Any extra information you're given, you don't use. In Chapter 6, if you're given the same problem, you might do it differently. But in Chapter 5, any extra information you ignore. So compute the sample statistic and the test statistic. All right, well, the sample statistic is given in the problem, right? It's this, so we're testing null of mu equals 71. So the statistic that goes with mu is x bar. So the sample statistic is just x bar. It's already computed for us. There are problems on the homework. You may have to compute it by hand. Or, not by hand, but on the calculator. But the test statistic is something else, right? We want to use the formula. Oh, wrong button. I can't really read this thing. There it is. Okay. So what I'm going to do is I'm going into this numerator-denominator mode. So on a TI-84, it's alpha stat plot. So it's F1, which is what we're trying to get to. And then you choose the first option, ND. And what it does is it just builds you a fraction. Right? If we go back here and look, we're trying to use this formula. So it's got a big fraction in it. You might as well just build out the formula. So sample statistic minus null parameter divided by the standard error. All right. So the sample statistic we've already established is 72. The null parameter, well, here's your null hypothesis. That's the parameter. That's the null parameter. That is a technical term that you were tested on chapter 4. So you've already been tested on that concept. It's 71. And, of course, we need the standard error, 0.467. Now, if you type it in just like this, it'll do all the work for you. Hit enter. You're done. So that's our test statistic. So if you want to try it again, try it on your own, pause the video. If not, we're going to roll ahead. Look at part B now. Using the standard normal distribution, find and interpret a p-value for this test in context. Well, we still got to draw the picture by hand. I am telling you, if you get in the habit of not drawing these pictures, it will come back to backfire because of how complicated this stuff gets in Chapter 6. So we know it's a right tail, and we know where 2.14 is on the graph. So let's go back to our whiteboard. I might be able to just back this up. Here we go. So 2.14 is over here just to the right. Right. 2.14. And it's a right tail. And then I just draw an arrow saying that the tail is just going. Well, we know what to type into the calculator now because we did one like this. So, second vars is distributions. We're going normal CDF. Lower. Well, this is a right tail, so the lower is the left endpoint, which is 2.14. The upper, that's our right endpoint, just big number. Doesn't matter what it is. 100,000 is fine. We're already in the standard normal, 0, 1, so we're good there. Paste. And you get 0.016. So one thing that's nice to do sometimes is just like write it on here. And just check it and say, does this look like a very small portion of the graph? Yes. Does it look like 1.6%? Pretty much. Just kind of check your work. Right, so we did that. You already know how to do this in StatKey. Here's how I did it on the calculator. Obviously, you saw me just do it. And in StatKey, it's the same thing, right? We know how to do this in StatKey. So there's your p-value. And from there, you would reject or do not reject the null based on the significance value. And so on and so forth, as you've done already in Chapter 4. So once you get the p-value, it's exactly the same as Chapter 4. So it sets up the same as Chapter 4. If you have to find your null and alternative hypotheses on your own, it looks like a problem in Chapter 4. Once you get the p-value, it finishes like a problem in Chapter 4. Compare the p-value to alpha, reject or do not reject, conclude or do not conclude the alternative hypothesis. And that's how it goes. So this is just an intermediate step where we can use the calculator to get an answer. And if you're doing these at home, maybe do both. Maybe do graphing calculator and StatKey just to check your answers. Okay, let's do another one. So I'm kind of doing these in rapid fire succession just to kind of show you how it works, sort of in real life. All right. Test P1 equals P2 versus P1 not equal to P2 when the sample has N1 equals 76, N2 equals 91, P hat 1 equals 0.145, P hat 2 equals 0.220, and the standard error is 0.06. Oh boy, there's a lot going on here. So what you might want to look at is the parameter here. So we're given the hypotheses, we're not given the parameter. Find the parameter first and then, work backwards to the sample statistic. So the parameter is P1 minus P2. Therefore, the sample statistic is P hat 1 minus P hat 2. Well, we have P hat 1 and P hat 2 right here. So I'm just going to type that in. So P hat 1 minus P hat 2 negative 0.045. So that's P hat 1 minus P hat 2. The test statistic, we use the same form we did before. So the generic version of the formula is sample statistic minus null parameter divided by the standard error. We are given the standard error. You have to be given that. And the null parameters you should be able to find based on what we did in Chapter 4. So P hat 1 minus P hat 2, that's our sample statistic. We just computed that to be negative 0.075. What's the null parameter here? If you're not sure, pause and think about it. Okay, so null parameter is 0. Did I do a minus there? What did I do there? Oh, I did not mean to do that. Oh, yeah, here we go. I think I clicked on the wrong button. There it is. Okay. Yeah, so if you use one of these graphing calculator apps, sometimes there it goes. Sometimes it doesn't translate properly. There we go. So negative 0.075 minus 0 divided by 0.06, and just get negative 0.125. We're not done. We have to draw the picture, look at the alternative hypothesis, and then go get us a p-value. Again, I'm doing the p-values on the calculator. Feel free to do them on StatKey on your own time. So you can see here that the alternative hypothesis is two-tail, and there's our test statistic. All right, so negative 1.25 is like right about here. On a two-tailed distribution, you always shade to the outside, right? Now what I do is I just go ahead and find the left tail, and then I'm just going to double it. So this part over here, you're going to have one part here, whatever the p-value is, and then it's going to be times 2, because we're sort of getting this part over here. I don't need to do the p-value over there. I'm just going to get a single p-value and multiply it by 2. So normal PDF. This is a left tail, right? Left tail. That means the lower, so this thing just goes all the way to the left. It just keeps going. So I have to type in a really big negative number. So negative 10,000 is fine. 100,000 doesn't matter. The upper is the right endpoint. So that's where it stops here at negative 1.25. 0 and 1 stay the same. And you get 0.105. And all I'm going to do, 0.106. Look at me not rounding properly. 0.106. I'm just going to multiply that by 2, and I'm going to get 0.212. Quick note, if you're rounding to 3 decimal places, whatever StatKey says, when you do it in StatKey, use the rounding from StatKey, which is usually 3 decimal places. Because if you double this value first, it rounds to 0.211, but the correct answer is 0.212. StatKey wants you to round first. So when you do it on the calculator, you have to round it to 3 decimal places, then multiply by 2. I don't think you're going to get it wrong if you're off by like 1 little decimal place, but you never know, right? You do have robots grading your homework. Okay, so that's the answer, 0.212. And it says interpret a p-value. So the interpretation of a p-value just means the probability of getting a test statistic at or more extreme than the observed negative 0.075 is 0.212. So make sure you can interpret p-values. I know you've already been tested on it, but the meaning of what a p-value is changes slightly over time as we pick up new techniques. The general idea is the same, but here we're talking about these theoretical distributions. All right, well, there's all the answers, right? As you can see, I did everything in StatKey and on the calculator, right? Here's the calculator. Here. All right, let's do one more. There's really not much else going on in this section. Oh, here's the null parameter values. This is a copy of the slide from Chapter 4. That is a reference slide for you. I'm not going to talk about it. So now let's do a full problem all the way through now that we more or less know what we're doing. In a smoking cessation program, 2,070 smokers who were trying to quit were randomly assigned to either a group program or an individual program. After 6 months in the program, 148 of the 1,080 in the group program were successfully abstaining from smoking, while 120 of the 990 in the individual program were successful. Do the data provide evidence of a difference in the proportion able to quit smoking between smokers in a group program and smokers in an individual program? So I'm going to move on in the slides. If you want to write this information down and work it out on paper, it's never a bad idea. So we need null and alternative hypotheses, notation, and value of the sample statistic. Then we're going to use a randomization distribution and the observed sample statistic to find the p-value. So parts A and B are things you did in Chapter 4. What we're going to do in Part C is we're going to use the standard error from our randomization distribution. Then we're going to use that standard error to do it on the calculator and on StatKey as well. So I know that seems like a lot of work just to do one problem, but the idea is that these standard errors come from the data, and that once we get the standard error, we can just pop over to the calculator and do it. That's sort of the idea. Or if you want to go back into StatKey and do it using the theoretical distributions, you can always do that. All right, so let's go look at it. Null and alternative hypotheses. Well, as you can see, there's a lot going on here. So we have smokers trying to quit. There are 2 programs. And the variable, so the response variable then is these people are trying to quit, and so they either quit or they didn't. So our explanatory variable is which group they were in. Are they in the group program or the individual program? And did they quit or not? So 2 categorical variables means that the null hypothesis is that P1 equals P2, and the alternative hypothesis is that either P1 is greater maybe, or P1 is less, or maybe it's just not equal to P2. But notice that we're told, do the data provide evidence of a difference? Difference means not equal, so our alternative hypothesis will be not equal. Right, so I called it group program and individual program. So the sample statistic, it just matches, right? If this is PG and PI, then the sample statistic is PG minus PI. And you just type all the data in. Again, I'm going to kind of show you again how to do this. Use this fraction thing, 148 over 1080. And then all you do is hit the right arrow. Do you see how I did that? So watch, right arrow, put in a minus sign, and then just do another fraction. Now, you can use division. It doesn't make any difference. It's up to you, whatever you're comfortable with, but I say why not use the fraction? Like, you're not saving any time by not using it. Right, and you can see it's 0.0158. I rounded it to 3 decimal places. Follow the instructions on the homework. Most of the homework is 3 decimal places. Every once in a while, there's a weird problem where it says keep 4. Whatever it says to keep, that's what you keep. All right, so we have our sample statistic. 0.016. Now use a randomization distribution and the observed sample statistic to find the p-value. So we're not going to do the theoretical distribution yet. We're going to go and do a randomization distribution and pull out the standard error after we do the randomization to get a p-value. So watch how this works. It's all in the notes, but I'm showing you live here. So we're just going to go back. This is a difference in proportions, right? So we're doing a randomization hypothesis test for difference in proportions. We have to put the data in, right? So, you know, it's good that it's already in the calculator, right? 148 out of 1080. I know it's super small, but you guys can follow along with the home edition. And the other one is 120 out of 990. Notice all that does is give us the sample statistic over here. You can see it. Oop, right there. Now, the null hypothesis is always equals. In this case, the alternative hypothesis tells us our tails. We're ready to go. We're just going to generate a bunch of samples. You can do as many as you want. In the PowerPoints, I did 10,000. So we can go ahead and do 10,000. And I know it's annoying to click this thing over and over again. But because we're going to use this standard error to do other calculations, we want it to be more precise. Now, it's not going to be exactly perfect. But the idea is that it's going to be good. It's going to be a good approximation. Okay. So there's 10,000 samples. Let's zoom in a little bit, just so you guys can see a little bit better. Our alternative hypothesis was not equal, so we click two-tailed. Yeah, you can see that this thing's using a lot of resources on my computer because I generated so many samples. Hope I didn't lock it up. Yeah, I might have to do it again. I have so many programs running on my computer right now. I'll give it a sec. I might need to restart it. That's okay. Oh, yeah, it's locked up. That's great. Yeah, that's fine. So you might want to fast forward this video fast forward the video until you see this thing kind of go red. All right. Okay, so it was 148 out of 1080. And 120 out of 990. All right, I'm only going to do 1,000 samples this time. It doesn't have to match exactly. Just with all these I got like 6 programs running on my computer. It's bogging it down, and so it's too hard to do a live video. So two-tail, there we go. And then you type in the original sample statistic. Again, it always appears here. So type in 0.016. Right, and you can see that our p-value is, you know, the right side, and it's a two-tail, so we double it. So our p-value is around 0.25, right? Because it's 0.125 doubled. But what we really want is this standard error here. We're going to use this, and if you guys are following along in StatKey, doing it like off to the side, you might have a different standard error depending on just like how random the calculations are. It just has to be close. Right, as you can see, when I ran the simulation for the notes, I did 10,000 samples and got the exact same answer. Slightly different standard error, though, and that's fine. Again, it's going to be a little bit off. So what we're going to do now, I'm just going to use this standard error here, 0.015, because it's the one from the notes. If you guys are following along, you might get a slightly different standard error, too. And we already know what the shape is, right? We know that the shape, let me just back this up a little bit, basically looks like this thing, right? It's two-tailed, right? And the sample statistic is 0.016. But the shape is going to look the same. But we don't know what the test statistic is. So we have to compute that, right? So this is what we do. Oh, where'd my calculator go? All right. So we're just going to use the same formula we used before. And this one's real similar to the last one I did. Right? If you the other one with the p-hats. So it's just going to be sample statistic minus the null parameter divided by the standard error. So we get our sample statistic, 0.016. The null parameter for difference in proportions is 0. And I'm going to use this standard error here, 0.015. Again, if you get a slightly different number, it's going to be fine. And I got 1.067. So this is my z-score. So when I draw my picture, I go over to 1.067, which is just to the right of 1. You always shade to the outside on a two-tail. So this is 1.067. And we're going to eventually get like this other half, but it's just going to be from the times 2 that we get, whatever the p-value is. So same stuff we've been doing. Second vars, normal CDF. So our test statistic is on the right side, so we're going to do a right tail. So the lower is 1.067. Let me double check the number of digits I'm supposed to keep for this answer. Yep, that's right. Again, each homework problem is different, so I just want to double check. So this thing just goes on and on to the right. So the upper is just some big number. Again, 10,000, whatever you want to. 100,000, a million, it's fine. A billion. So we're finding this area here, which will give us this p-value. 0.143. And then we're going to multiply it by 2. So we're going to get 0.286. And you can see that on the slide, exact same numbers. Notice that the p-values don't exactly match, right? This one was 0.25, this one was 0.286. This is not an exact science. Because we use random distributions, there's some variability. As long as you're close, you'll get it right. Now, we have to compare it to alpha. So we were given, in the original problem, part D, use the standard error found from the randomization distribution to find the standardized test statistic, and use that test statistic to find the p-value. And we already did all that, but notice that we want to continue on and reject the null hypothesis or do not reject. And that's what I did at the bottom. That's sort of a follow-up question. So because we have a large p-value, that does not give us sufficient evidence to reject the null, so we cannot conclude a difference exists between the quitting rates of the group program and the individual program. So even though the sample statistics showed there was a difference, based on the standard error, there's too much variability, right? And so essentially too many of the dots are red. So a lot of red dots means large p-value. Because that's what a p-value is for this. And then when we did it here, the p-value, we just overlaid a smooth distribution and just counted what proportion was occupied. And that's it. That's all you're going to have to do in this section. So when you're doing the homework, we're running through these examples again. Keep calculator handy and stat key rolling, and just check your answers as you go. If you have any problems, you can email me, of course. So the last thing we want to touch on here before wrapping it up for this session is why are we introducing another new way of solving problems? Because that might seem just like a lot of extra work. Randomization distributions work fine. Why are we doing something different? So that's explained by my 2 bullets at the bottom. Randomization distributions are useful for understanding the notation and how everything fits together, but they aren't necessary for computing p-values. Once we understand why the methods work, using a graphing calculator is generally much easier. And that's sort of the bottom line here, is if we can avoid using StatKey altogether, we would like to do that. But we have to be able to demonstrate that the graphing calculator is capable of giving us maybe not the exact same answer, but a comparable answer. And that's really how this works. All right, that's the end. Make sure you learn all this stuff. Here's some extra problems for you to work on in the book and the ebook. All that stuff is posted and you can do it. And next session, we will be looking at section 5.2. If you have any questions, shoot me an email, go to tutoring, or I'll just see you in class. And I will see you next video. Bye-bye.